So the title of this talk is California's Water, Insurmountable Opportunities. And this title, Insurmountable Opportunities, comes from an old Pogo Possum cartoon in the 1950s. There was, those of you that are old enough, maybe you have seen those old cartoons. It was sort of the Doonesbury cartoons of the 1950s during the time of the communist conspiracies and everything like that, all the messiness. And there's the central character was a fellow named Pogo Possum, who was a little cartoon character. He lived in the Okefenokee swamps in Florida and Georgia. And he had these wonderful little witticisms. And one of them was, we are confronted with insurmountable opportunities. We are often in California water thinking about problems. People love to talk about problems. People talk about so many problems, they think that nothing can be done. Well, that's actually not the history of California water. The history of California water is one of insurmountable opportunities, where there are an awful lot of problems, and somehow we get through them all. Well, not all of them, but through enough of them that we make progress. So I kind of like it as a title. It's a little bit whimsical and a little bit of fun. Where to begin? So when you're talking about California water, it's such a big subject, you're always wondering where to begin. And you know, for those of you that go out and work in this field, this is where most of your conversations will begin. I don't care whether you're talking to the public or even many elected officials. This is what they understand about water. How do we get water into our homes? Well, I turn the spigot and water comes out, clean water, potable water. And where did that water come from? Well, it came from precipitation sometime, someplace, right? But in the middle, it's really hard. So I think we always have to realize that when we're talking to most people, and most of you are not most people, hopefully most of you have some vague idea what goes on in this box. But most people don't. And I'm not even sure that people that have worked on this for 30 years have a complete understanding of what's in that box. So don't think you're at a disadvantage compared to anybody else. Well, so here's sort of where that box is. This map shows where the runoff comes from in California. And I think this is really, really interesting. As someone that comes from the East Coast, where I encountered abrupt climate change when I moved to California. The dark blue areas here is the 20% of California's land area that provides 2/3 of the water supply.
So I have fresh batteries. Fresh batteries.
The red area here is the 30% of California's surface area that provides 0.1% of the water supply. Where is that water falling? It's in the north. And what time of the year does it fall? In the winter. Where's the water demand? Human water demand in this system? It's almost identified by this red zone here, you know, and up in the Central Valley, and then in the big cities here, and then especially down here. Not so much out of there, that's all desert. Although down here we have another big irrigation area. Imperial irrigation. So, and when are these water demands occurring? In the summer. So here we have all of our water is in the north, in the mountains, in the winter. And when and where we want the water is in the south, in the summer. This is a system made for engineers. Mm-hmm. So here's where the people are. You can see the greater sort of Sacramento, Bakersfield metropolitan area that's developing along Los Angeles. Here's when the runoff would occur naturally. So this would be unimpaired flow out of the delta. The blue is the wettest year on record, 1983, almost 72 million acre feet of runoff. The average is in the green, and the red is the lowest year of record, 1977, water year, almost about 5.5 million acres worth of flow. So you can see we have a lot of variability between the wettest years and the driest years. And we always have this tremendous seasonality of December through March is really when things precipitate, when we have rainfall and snowfall. And then April, May, June is sort of snow melt. Most of this is snow melt. And then when we get down to August and September, it's hardly anything at all. October, hardly anything at all. Then it starts to increase. Tremendous seasonality, tremendous interannual variability. This picture is Oroville Spillway working. I think it's during one of the flood events. So this map here shows essentially some of that mismatch. The blue is the water availability. That's sort of the average annual water availability in different regions in California. And then the colorful staff here is the relative environmental, urban, and agricultural water demands, water uses. And you'll notice we have more water available in the north. In the north, we tend to have more environmental uses, more agricultural uses. We move to the south, things are sort of balanced. The San Francisco Bay Area, about a match, but a fair bit of urban use. When we get down to the Tulare Basin, they use more water than they have. Oh, how do you do that? How do you do that? How many of you are familiar with conservation of mass? How do you do that? You got to bring it in from somewhere else. So Tulare is a net importer of water. They bring a lot of extra water. They divert the San Joaquin River. They bring it down. They have the California aqueduct that brings it down, and the Delta Canal that brings it down. Well, if you're taking a lot of this water from the San Joaquin River, that means there's actually less water here. And so some of the San Joaquin River area, they get water from north of the Delta through the Delta Canal. Lahontan's about the same. Colorado River has a lot of agricultural use. This water availability here doesn't count the flow that's coming down the Colorado River that California has access to, and so they import water from the Colorado River to make this up. And the South Coast here, big urban water demand brings in water from the Colorado River and all the way north from the Delta, as well as from the South Lahontan area with, maybe some of you have ever heard of Owens Valley or Mono Lake. They want water from Mono Lake and they don't. Well, hardly all. So there's the mismatch. And here's a set of infrastructure we have built over decades, over 100 years, to sort of reconcile this mismatch of time and space and location. So you'll see a tremendous network. And I really like this map because it's so colorful. And it's so many neat shapes on it. So all the triangles are reservoirs. And you can see up in the mountains, there's a whole big long strings of reservoirs. And then to move water from the north to the south and from the east to the west, we have all these aqueducts. And there's so many different colors here. Why would they be so many different colors? Because they're all owned by different people. I often tell, particularly foreign students, when they come to California and start to study California water problems, I tell them, in the United States, we hate government so much we have thousands of them. And nowhere else is this so true as in California water. So you'll see a lot of green lines, which are all owned by different local agencies. So an awful lot of the early development was Los Angeles Aqueduct, Metropolitan Water District, Pachechi with San Francisco, McCulney River with East Bay Mud, local irrigation diversions up here. Then we have federal water projects, which are in black, the same color as the helicopter. And so we have some fairly big infrastructure, and you can see the thickness of those are a fair bit of water moved. And then we have the state projects, which are in gold, the golden states, so they're golden. Particularly the California Aqueduct that moves water from north to south. Tremendous reservoirs of inches. Now, sort of the minority color here is blue. Oh, that's the natural river. That's the Sacramento River. The San Joaquin River, there's hardly anything left of it. It's more of a drain now. These blue dots are hydropower. About 15 to 25% of California's electricity comes out of hydropower, depending upon how wet the year is. So we have an awful lot of hydropower scattered throughout the system, particularly, certainly up in the mountains. And then there's a tremendous agricultural area down here. So really an amazingly intertied, hugely diverse network of California's water system. And it's all owned and operated by about 1,000 to 3,000 different water districts. So tremendous decentralization in terms of local ownership. And then with, of course, tremendously important also state and federal involvement. Sure.
How is it decided if it's going to be a state, federal, or local project?
Whoever got to it first.
But they still have to comply with all of the state
Most,
water board.
most of these things were built before there was anything to comply with.
Okay.
So almost all this infrastructure was built before the environmental legislation really came into being. Just one example of this is the state water project. This is not the largest project, but it's the most geographically extensive. You can take water all the way from the way far north of the state and send it all the way down, essentially, once you connect it up locally, down to San Diego. And actually, I understand there's infrastructure. You could even take it down to Tijuana if you wanted to. And you can see in terms of elevation, water is released from Lake Oroville, generates a little bit of hydropower, flows down the Sacramento River, is pumped up the delta, then pumped up some more, pretty high, and then they make hydropower on the way back down. So it's really kind of amazing projects. Water supply is not our only problem. We also have good floods here. So this is a great place to get water, which is why many of you are here. So this is the Sacramento bypass system as an example of that. So the Sacramento River, there's really two Sacramento rivers. There's the low-flow Sacramento River, which is what you see between the levees in the summertime. And then that long causeway that you drive across to get to Sacramento from here? That's the flood bypass down about here. In terms of channel capacity, the main stem of the Sacramento River down by Sacramento is about 130,000 cubic feet per second. So that's about a CFS, for those of you that are not in technical fields, is essentially a volume equivalent to a basketball every second. So think of it as 130,000 basketballs per second. Just try to count as they go by. The flood bypass, that big long causeway, has a capacity of 500,000 cubic feet per second. So by far the majority of the channel capacity of the Sacramento River Valley is in the bypass system. To try to put all of that through that narrow channel that we use for the regular Sacramento system, we have lots of floods, which is why they built the bypass system. Still, Sacramento Valley has some major areas that are flood prone. Sacramento, the Thomas area, certainly the biggest of those. It's listed as among the top flood-prone areas, urban flood-prone areas in the country still. Then we have up by Marysville, Yuba City, another major flood-prone area. This is in the flood of 1955. That's Marysville. This is before Lake Oroville was built. So this helps explain why Yuba County was so very favorable to the state water project. They wanted to avoid seeing this. And then we have some problems here down in Woodland, and then smaller ones down in Clarksburg and many of the small towns along there. In terms of the major urban concentrations of flood-prone areas, they're in these red zones. And here's the bypass just a couple of years ago. You can see where it's full. Close to full. We've modified California's water system tremendously, and it's always been changing. I think it's important to understand how dynamic the landscape is in geologic time here. This is a map of California about 1600 BC, basically at the end of the last ice age. At the end of the last ice age, sea level was a lot lower because there were still all these glaciers everywhere. Sacramento-San Joaquin Delta was out here, outside the Golden Gate. And then as the sea level rose, that delta moved inland. As it moved inland, it drowned out at the confluence here. So essentially, what we call the delta is really more of a drowned confluence, I think in geologic terms. And it's continuing to drown as sea level rises. And as islands subside. 1873 is one of the earliest maps of the Central Valley. You can see very large gray areas on this map. And these, you can't read the key at all, but these are overflowed lands. So we had tremendous, permanently inundated tidal marsh in the delta area, and then we had tremendous seasonal floodplain. Seasonal, maybe some of it was permanent, depending on, because some of the groundwater tables were much higher as well, so they tend to drain less. Those of you that have ever driven up and down the valley know this is a very, very large, flat place, and so water tends to puddle, which is part of our flood control problem and part of the wetlands that originally were here. And of course, all of the native birds and fishes evolved into this landscape, which we've done a lot of changing. Well, some of the changes we've made in terms of the environmental side, we've put a lot of dams in. So this map here shows the extent of salmonid habitat. And you can see the areas, the red areas that are no longer accessible or no longer active habitat for salmon. Tremendous losses of streams, largely because of dams, particularly for the upper spawning areas. With climate warming, what would you like to see fish do? You'd like to see them migrate to higher and spawn at higher elevations where it will still be colder. But if you can't get up there, then I think that's going to impose problems for that natural adaptation that these species will try to do. What's not so much shown so much here is a tremendous amount of rearing habitat that has been blocked off when we levied all of the lands that naturally flooded. So you can see on this map, the yellow area was the extent of wetlands in 1900, and you can see that almost all of it is gone today. Only that little red area, bits of the Suisun Marsh, and a few other small areas, grasslands irrigation district, are left as wetlands. We've had a little bit of a substitute for wetlands in terms of rice cultivation. So you'll see the gray areas up in the Sacramento Valley. We have a lot of essentially rice land habitat for waterfowl, migratory waterfowl that exists now, but didn't all exist before. It was in that big yellow area, now it's in that gray area. And most of that rice land is, of course, not available for fish, so it's worked out better for the birds than for the fish. We still have growing urbanization, so you'll see here some projections that go up to 2050, again, of the greater Bakersfield, the Sacramento metropolitan area that's forming across along 9, growth in Southern California and the Bay Area. I mentioned some of the seasonality. This shows the average seasonal flows over different historical periods. So you can see in the San Joaquin, the 1921 to 2003 unimpaired flow averages, and then historical periods from 1949 to 68 to 1986 to 2005, where we've essentially been capturing the winter-spring peaks, diverting it onto agricultural fields, storing it in reservoirs for use later in the season. So we have much more muted spring flows than we did before. I think it's also interesting in the summer. So here's the San Joaquin River, which is tremendously depleted overall. It's probably about half of what it used to be in total flow. Notice in the summer, it's actually flowing a little bit more than it would naturally. It's a lot saltier too. A lot of drainage water. In the Sacramento Valley, there's a lot larger flow. You'll notice the scale is twice as big. So it hasn't been as big of an impact. Here we have a lot more water flowing in the Sacramento River into the Delta than we would have naturally. Why is that? How would we possibly have more water flowing down the Sacramento River into the Delta in the summer than we used to have? It's reservoir releases, right? We captured all that water in the wintertime, and we're releasing it in the summertime. Where's that water destined to? Is that going to flow out the Golden Gate Bridge? It's going to be picked up in the South Delta and pumped to the Bay Area and to Southern California. So in some places we have more flow than we would have had naturally, but the pattern is not natural. One of the lessons. One overall result of this is the fish are sort of losing in all of this. These are some results from Peter Moyle, who's in the back. I'm going to keep him awake. 1986 is sort of first survey out of about 130 freshwater native fish species. About 4 of them were doing fine. 7 were extinct. 14 were listed. About 50 were sort of a little bit worried about them. 2010, we have half as many species are in good shape. The number of concern have been going up. The number of listed ones is more than doubled. We haven't had any more extinctions. What's up with this? I mean, this is 1989 to 2010. We've had decades since the Endangered Species Act, decades since the Clean Water Act came in. We've had a lot of big improvements. How come the fish are getting worse? This is a big problem. So we have a widespread decline despite decades of well-intentioned effort. These listings are now affecting our ability to run water supply systems and flood protection systems. And we can probably expect these conditions to worsen with additional climate warming and additional invasive species. So it's not, what we've done is probably good on the environment, but we haven't really succeeded by a long shot. Some of the changing water challenges in California. Here's how the economy of California has changed over time. Back in 1850, about 75% of employment in California was in the mining industry. How many people here are thinking they're going to go work in the mining industry? Okay, where's that gone? Well, first of all, California's population is huge now compared to people. You'll see this huge drop in mining in this area here. Partly this is the depletion of the gold fields. Partly this is the growth of other kinds of economic activity, particularly agriculture. There's a famous court case in the 1880s where basically the judge shut down hydraulic mining, saying that the sluicing down of hillsides in order to mine for gold was causing more damage to the economic development of California than it was worth. Basically, it was impeding the development of agriculture. And so we basically shut off a significant portion of California's economy at that time in order to let another part of the economy grow. In this case, it was agriculture. What we've seen over time now, the overall growth in California's population and economy is a declining share of agriculture, just as we had a continuing declining share in mining, and a shift in water demands to some of these other purposes, some of these other uses. You see California's population growing. So one of my arguments here is that the changing economic structure of California is what drives our purposes for water management. We used to manage primarily for mining. If you go back to the early water law for California, the early water technologies, it was all to manage water for mining, then managing water for agriculture. Now we're interested in managing water, certainly for agriculture, but more for urban and more increasingly for environmental purposes. A little bit of history. Trying to organize the history of it. This is very confusing, which in fact is true. History. We call it Floods, Droughts, and Lawsuits. There's a chapter in our book on history of California water, entitled Floods, Droughts, and Lawsuits, because the history of California water is periods of conflict punctuated by floods, droughts, and lawsuits, where you have a high enough level of political attention that politicians are willing to actually make decisions and see them through. And that usually requires a flood, drought, and lawsuit. In the early period of California water was an era we called laissez-faire. Now imagine you were coming over the Sierras or arriving by clipper ship and you came to California. Where would you be coming from? The Midwest, the East Coast. What's the climate like there? Cold. What a California response. It was wet. Sure, it was cold too in the winter. It was humid. Most of the rainfall was in the summer. How did you irrigate your fields in the east? Because remember, the economy was primarily agricultural. You used solar desalinated seawater. Rain. You came to California. You settled by the banks of the Sacramento River. You thought, oh, good, we made it through the summer. There wasn't any rain, but I was able to get a little bit of water out to water my field have a small crop. Then what happens in the winter? Then it rains, and you say, wait, it's not supposed to flood in the winter. It's supposed to flood in the summer. That's where I came from. In this laissez-faire period, people are trying to organize themselves. Little groups here, little groups there, individual farmers here and there. It didn't work very well. You ever try to build a levee by yourself? It doesn't work very well. You want to try to build a water diversion by yourself? It doesn't work very well. So there was a period following that of what we call local organization, where you had levee districts formed, and irrigation districts formed, and municipal water supplies developing and bringing in water. So in the Sacramento Valley, there's a wonderful book by Robert Kelly called Battling the Inland Sea on this. You had levee districts forming on either side of the river. So if you're a levee district, how high does your levee have to be? Higher than the guy across the river. From his perspective, how high does his levee have to be? So the game theory of it is like this, right? Well, and then someone discovers dynamite. Because my levee doesn't always have to be higher than your levee, only during a flood event. And so you end up with basically this kind of guerrilla warfare happening during flood events. And eventually the state says, enough's enough of this. This isn't actually working. And so we sort of enter into this hydraulic era where the state and federal governments come in and say, okay, this local development isn't enough. The proper scale for governance and managing of the system is at a larger scale. We have to manage floods in the Sacramento Valley, not at the local parcel scale or the local district scale, but at the valley scale. And so you see large bypass systems coming in, you see large irrigation systems, large reservoir systems and canal systems coming in. And we spent decades building that stuff under federal and state governmental power. What happens towards the end of that time? Towards the end of this time, almost all the rivers already have reservoirs on them. So if you want to build a new reservoir to get more water, which is sort of a knee-jerk reaction of most people, you have a water supply problem? Oh, let's go build a reservoir. That's what we did for decades. Now there's no more sites that don't have reservoirs. Well, there are sites, but they're really expensive ones because you already built the reservoirs on the cheap sites, the ones that were going to yield you the most water. Now we're down to a few remaining sites that are really expensive to build at and don't give you a lot of water. So this sort of peters out for economic reasons as well as tremendous environmental interests, because we're starting to see the scarcity of the environmental things that we didn't value so much when we were poor, but now that we're relatively rich, we start to value. So now we're sort of in this era of conflict where we're trying to sort all this out. And in our book, Peter, one of the co-authors here, and some other people that have worked on this here, we're hoping for an era of reconciliation that comes later. We have a lot of objectives in water management here. California, so a lot of different water supplies. So it's not that water supply fights with floods, fights with environmental habitat, fights with hydropower, fights with recreation. There's also fights within each of these groups. So the different agricultural users don't like other agricultural users, don't like urban users. The north hates the south, and it's really the civil war all over again. Well, not quite civil war. Floods, we sometimes have flood versus flood interests. Oh gosh, you can't raise your levee because if you raise your levee, you're going to increase my flooding. All this kind of stuff. So it's really an interesting system. And it's always changing. I mean, I think from the slides I had before on history, I think you can see how this system has changed in very fundamental ways over a century and a half. And it's going to continue to change. So we're going to see changes in climate, sea level rise, warming, changes in precipitation. We have sort of deterioration that is occurring because we've been here a long time. We have aging infrastructure. We have accumulations of contaminants, salts, nitrates. Tom Young here can probably give you a big long list of other things. We have sort of legacies of the mining era still. We have a lot of mercury contamination in different parts of the system. We have accumulated groundwater overdraft in a few places of the system. And we also have lower groundwater tables in general in the whole system because we've been using groundwater. Earthquakes. Earthquakes are not good, particularly I think they're pretty bad for the Delta, and we'll have continuing deterioration in the Sacramento-San Joaquin Delta for a number of reasons. We have change in the economy and demography. Again, the changing economic structure, globalization, the deterioration of the state and federal government's ability to finance anything, ability to lead things, and then continued population growth and urbanization. We have really changes in ecosystems that are pretty fundamental. Continuing additions of invasive species. About 90% of, if you go scoop up a bunch of biomass in the Delta, about 90% of that is invasive species. How many Native Americans are here? Okay, so you can see the effect of invasive species on the population. And we have continued degradation from a wide variety. We have changes in science and technology. We have new chemicals that are coming in, being used in widespread ways all over the place. We have new technologies, computer modeling, remote sensing, new water conservation technology, a lot of good things too. So all these changes aren't all bad. Some of them are actually pretty good. I want to talk a little bit about the Delta. The Delta is sort of the problem du jour in California for about 80 years. It might not change over the next 80 years. Delta is right here in the middle of this network. If you want to move water north to south, it's going to involve the Delta. In the climate change studies we've done, also in the slide later, it becomes even more important. Everybody depends on the Delta. Some people live in the Delta and they depend on the Delta because they live there. Some people are south of the Delta or west of the Delta that depend on the Delta because they take water directly from it. We, in the northern part of the Delta, north of the Delta, we're dependent on the Delta because we take water before it would have gone there. So if there's higher inflow requirements for the Delta, it's a likelihood that we're going to be asked to surrender some of our water use as well as everybody else. Because we are all taking a lot of water, as you can sort of see from these numbers. It's not just Southern California. We like to blame Southern California. Certainly they're guilty of sin, but we're not completely without sin ourselves. Problems of the Sacramento-San Joaquin Delta. First, there's a problem of physical instability. The Delta, as I said before, was formed with the submergence, essentially the inundation of this confluence of the Sacramento and San Joaquin rivers. The land essentially kept up with that inundation by the accretion of tule marsh. So tules would bring in carbon dioxide, they gather up the sediments, they die, and they add to the accretion of soil. As the sea level rose, the marsh would rise with it. So long as the sea level doesn't rise too fast, the marsh can keep up with it, and you sort of keep a tidal marsh at that location that expands. Those soils that come from that kind of geologic process are peat soils. They're partially oxidized decomposition material. And so what has happened in our delta is what happens in every peat marsh in the world. When you dike it and drain it, you're exposing those soils to oxygen again. And they complete their oxidation, and they go away. They oxidize, they literally go up into the air. It's carbon dioxide. Huge carbon sink, actually, that is no longer a carbon sink as much. We also, in addition to that, have sea level rise, another source of physical instability. Floods and earthquakes. So a lot of reasons to be concerned, particularly with these very low-lying parts of the delta. These very red areas are more than 15 foot below sea level. So if you're standing in them, you see ships going by. Ecosystem instability. Tremendous habitat alteration. We had 700,000 acres of tidal marsh here. We're probably down in the 50 or something like that. We're just way less. Maybe 95% of that's all marsh. In terms of the physical habitat. Certainly then, we've also tremendously modified the hydrologic habitat. The upstream diversions on the San Joaquin and the Sacramento River have a lot more salty discharges coming into the San Joaquin River. Invasive species. Tremendous numbers of invasive species coming by airplane, by ship ballast, by aquarium tank, by bait box, all kinds of things. Peter will probably have a lot to say on these in February. And then economic instability. You can go back to some of the really neat old literature of the 1950s where people talked about these settlement patterns, and they talk about, well, if you're running one of these islands, particularly one of the more subsided ones, that has relatively low value crops on it, and you're having to pump your drainage water higher and higher elevations to get it off your island so your crops don't drown, your costs are increasing as the sea level rises and the land subsides. Your costs are increasing. And if your island should fail, and Liberty Island in 1990, so basically 3 out of the 4 islands that have failed most recently, 2 out of the 3 islands that have failed most recently have been abandoned. Jones Tract failed in 2004 and was fixed. And that had a lot of valuable stuff on it. We have a lot of other regional problems outside the Delta. The Delta is not the only problem we have, not by a long shot. So we've got really interesting problems on the Klamath River system. Maybe some of you have heard about salmon, dams, and hydropower, and all kinds of stuff up there. Sacramento Valley also has flood problems. Every one of these regions has lots of really interesting problems, and we have a lot of groundwater problems of different sorts everywhere. I like this map showing water quality problems in different parts of California because it shows how each region has a little different kinds of problems in the state. So it's not like all of California has one problem, or even all of the Delta has one problem. Different parts of the Delta have different problems, different parts of California have different problems. And the whole state has problems. It's a great place to spend your life. So today's challenges, I try to organize these a little bit. The first challenge we have is the limitations of traditional management. If you go and talk to the average politician or the average person on the street, and you say, we have a water problem in California, what do you think we should do? They're going to go back to the time when they were growing up and say, oh, if we have a water problem, we should build another reservoir. Because that's what was done for all those decades. Well, there's very little reason to think that large-scale reservoir construction is going to solve hardly any of our problems. It might solve a few, but it's not going to be major. Our traditional management, we sort of reached the technological and economic and environmental ends of it, for the most part. We still have sort of major long-term problems. I think originally, in my wording in this, I had permanent problems. In some sense, at least for our lifetimes, they'll be permanent. Native species and their habitats, particularly wetlands. How are we going to restore these native habitats to the degree we can keep some of these native species? How do we reconcile permanent water scarcity? There's always going to be some water scarcity in California. There's a wonderful saying in water that there's no such thing as a water shortage. There's only a shortage of cheap water. Is there a shortage of oil? Sure. How do we know that? The price has been going up. Same thing for water. That's how our society tends to ration things, is with prices. So we need to figure out ways of reconciling this idea of permanent shortage. We have permanent shortages of a lot of things. Permanent scarcity. We'll need to figure out how to reconcile ourselves for water. Groundwater. We have depletion over time, particularly in the Tulare Basin and other places. We have essentially permanent degradation from salts accumulating in groundwater basins in some places, nitrate contamination occurring in many rural areas, and trying to figure out who owns the rights to water if we're going to manage it. And I think we have a major problem in that the state and federal governments are going to be basically permanently weak for a few decades at least. We really left the era when there was a lot of state and federal money to coax everybody along. There's going to still be some, but it's not going to be the major thing anymore. Most of the power, most of the money is at the local districts, local cities, local irrigation districts. We're going to have to figure out ways that induce them to cooperate and work together across this statewide system without having a lot of money to bribe them as we had in the California area in the past. Third major problem is how do we modernize the statewide system? Modernizing the local systems is pretty easy because they're pretty flush with money relative to other governments in California and the United States. But how do we modernize a statewide system? It's got to serve many different goals, many of which conflict, and many of which have a mutual need for each other. We have to figure out what to do with the Delta. The Delta is really the central, if you have one identifiable focus problem in California's water, then it is the Delta. we have to figure out how to rebuild it in a more sustainable way, or figure out how to abandon it and not depend on it at all for many things that we're used to. We have to develop locally driven portfolios of actions within a statewide system. So how much can each local area depend on water from the statewide system, both for flood control and for water supply? And how do we have the locals contribute to the statewide objectives on the environment in particular? And then challenges for state government and regulation. How is the state going to be involved in a system which is predominantly driven by locals? Some reasons for hope in all of this. I really like this graph. We did this when we started making the book. It's likely that human water use in California has peaked. For decades and decades, every California water plan, all thinking on California water was, oh, demand is going to grow. It's going to keep growing forever. We've sort of seen the end of that. We're not going to see major expansions in irrigated land areas. We're going to see contractions in irrigated land areas. Why? Some places it'll be accumulating salinity. In other places it'll be because urban areas are expanding on top of agriculture. In some areas it'll be because there's water shortage and they're going to not be growing stuff there. We will reallocate that water someplace else. The urban growth has sort of leveled off for a long time now. What's that from? You might remember a few slides back, the population increases are still going. They're slowing off a little bit. There's even some thought that population might even decrease in a few decades. But most of that is urban water conservation. A lot of that is urban water conservation. Smaller houses, smaller yards, less toilet water, things like that. Toilets are more efficient. So over time, it looks like we might have peaked. So I think that's a big reason for hope. We don't need to have these sort of, where we have an indefinite competition between people, zero-sum game over water, or negative-sum. Today's economic structure for California is less dependent on water than it was in the past. Back when agriculture was a third of California's economy, we were very dependent on water. We had a big segment of the economy that it required abundant, cheap water. Today, agriculture is about 5% of California's economy. It's bigger in absolute numbers than it was back when it was 30% of the total, but the total has gone so much higher. Okay. So if you look at the total economic disruption to California of the water shortage, of the drought, it's much less today than it would have been in the past. That gives you a reason for hope. We're a lot more stable, resilient economy in terms of water. Third, we're starting to develop water markets that can sort of more flexibly, let's say, a more civilized way, shift resources from a sector which is becoming less valuable relative to other sectors. Okay. So we can shift water from lower valued agriculture to higher valued agriculture, from lower valued agriculture to cities. And it's a way that compensates the farmers. So if the farmer has senior water rights, they get paid to make the shift, just like you would if you had a piece of land that you're just going to shift from one use to another. And I guess final reason for hope is we all agree we have a problem. This room is full. We're going to have to look at these portfolio-based management. It's not, if you have a water problem, you go build a reservoir. Now we have a whole bunch of different things that we can use to manage water. A lot of these are done locally. A lot of these are statewide. We really need to do some portfolio planning that looks at how do we mix these options over time between wet years and dry years in different locations in the state. We've done some modeling of this. This is a schematic of California's water system. I'll sort of unroll this quickly. This is my favorite visual image. So this is California's water system. Simple thing, isn't it? Remember this for the quiz. And so this, the point of this is to show that it is complex, but you can work your way through it. You know, if you look at a schematic for the electronics on an airplane, it makes this look really simple. But we fly airplanes all the time and we build a lot. They're pretty expensive, but we still do it. So we have a computer model called Calvin that we developed here and we try to use to help us integrate supplies and demands and different kinds of water uses and to see how things would work over time with different kinds of climate changes and all kinds of things.
So was the last slide an optional
No.
on the right? Is sort of
That's what we have today. That's that schematic put on top of a map of California. Calvin is wonderful. I really like the idea. He's sort of a mischievous 5-year-old and a strict disciplinarian at the same time. There's some math involved. Fish is trying to make sure quizzically what the heck is it? But what we're trying to do is take data that represent all the different water demands, the hydrology, the physical infrastructure, the costs of operation, put that in all together, run some optimization to see what looks economically promising. And what are the costs, and how do the environmental aspects work into the system? So we can look at costs of environmental flows and things like that. As part of this, we've had to develop economic values for water delivery. There are all kinds of uses all over the state. You can see for agriculture, the value of water delivery varies tremendously all over the state. You can see the really dark red areas are $150 to $300 an acre foot. And then some of these areas are much lower value for economic purposes. This is some results out of some recent study we've done that has changes in climate and changes in urban water conservation. So if you go up here, that's sort of where we are now, full exports, historical hydrology. If you have a much warmer, much drier climate, you see a lot more water scarcity coming up. Red is water shortages. If you end exports, shortages increase a lot. On the agricultural side, shortages increase a little bit. On the urban side, they're higher value. They'll buy water from the agriculture where they can. The purple here is all these sort of fancy wastewater reuse, desalination projects. If you add urban water conservation to this mix a lot, the expensive activities go away, so the urban guys hardly do wastewater reuse and desalination anymore. A lot of the shortages in agriculture decline, but under some circumstances, particularly where you end water exports and you have a much drier climate, there's still very, very large water shortages. So you can explore these in infinite amount of detail with computer models. And of course, we've done that. This is the graduate students. So where to end? Now we have computer models to help us understand a little bit, help us play with some of these ideas. Roles of the university. We're really in a very lucky place here at the University of California. We're right in the center of things, and we're not responsible for any of it, except for the water that we use. What can we do to help? We can try to understand this system. You see, I kind of like the Dutch movies. You have this Tower of Babel, and here we are in the middle of it. All these different stakeholders that have trouble talking to each other. We can educate students. That's the most important thing we do. We can say controversial things in useful ways. If you talk to people in agencies, there's a lot of things they know that they can't say. It'll cause too much political trouble. I've got tenure. No one in Sacramento was ever able to fire a graduate student. We can say what we think needs to be said. And if we say it in useful ways and we're diplomatic about it, we can be very useful. We can look for problems and we can assess solutions. Sometimes people aren't able to do that very freely in the stakeholder world. We can explore novel solutions. We can myth bust. There's all this folklore that occurs in Sacramento and elsewhere in North California water. We don't have to help hostage.
No, he won't need it.
We're particularly useful when the agencies fall silent. So when something is so controversial that the agencies can't be organized. When they're quiet, then they can listen for the university. But in many ways, I think universities have to become more effective in order to take on some of these roles. We're a little bit feudal in what we do. There's ways that we can do that. So some conclusions. We have a statewide water system with local governance and fragmented regulation. There's very limited state and federal abilities to come in and solve these problems. They're very important, will be crucial, but much less capability than we've had in the past, than we're used to in many ways. Local government is really the most important. We have to figure out ways to make that work at the statewide scale. Complexity enriches possibilities. People often talk about complex systems being brittle. Actually, no. If you've got a complex system, there's a lot more ways you can work around problems than if you have a simple system. Give me a complex system any day, as long as I have enough time to figure out the maze. Integrated portfolios of all these different management activities are the future. My favorites here. Nature and economics eventually prevail over indecision in existing law. This has been true for every era of California water, every era of environmentalism. Eventually, we figure it out after we've done everything else. And then universities. If you want to read what I think is an outstanding book of this, Professor Muir in the back, and me and a few other people on the campus wrote a book a couple of years ago now called Managing California's Water. This book is really outstanding in that it's free. So you can get it free off the internet, or you can pay, I think, $35 to get a physical, heavy, bulky, tree-killing copy. But I want to highlight this wonderful collaboration with biologists and economists and engineers and geologists and lawyers that went into this work. We tried to write it so it would be useful for people. So download it, read a few chapters if you want to read some more. So here's some more suggested readings. There's a lot of wonderful stuff written about California water. A few things that we've written on California and the Delta. Some wonderful histories, Hunley's Great Thirst, Kelly's Battling the Inland Sea, which I think is just a wonderful book. Pisani's now sadly have a print history of irrigation in California. We have a couple of fun blogs, California and California Water Blog, that we write out of the Watershed. I want to ask you, what do you think this map is of? This is the map of the votes in 1982 on the Brookfield Canal. I'm originally a cultural geographer. You wouldn't really know it from that, but when I look at this as a cultural geographer, you know what it says to me? Does it say anything about the Brookfield Canal? No. Yeah. How many of you think really deeply before you vote on an issue? Okay, we're at the 1 percentile here. So, what it really says to me as a cultural geographer is Northern California doesn't like Southern California. And it might be reciprocal. Anyway, thank you all very much.